Good morning, everyone. My name is Min.
My name is Rachel.
My name is Helen, and today we're presenting on the topic of analyzing quantitative data.
Everywhere we look, numerical data can be found, from as simple as our grades to the trends of COVID-19. And statistics is a pivotal part of this. It's a group of procedures that enable us to find patterns and meaning in the numerical data. It makes us ask, what does this data mean? What does it communicate? And today we'll be investigating ways to analyze quantitative data. One of the first steps in analyzing quantitative data is you got to know how to explore and organize your own data set. Look at your data, look for patterns in the numbers with an open mind and your imagination. Look critically and inquiringly. For instance, in my own research on clinical facilities, I want to look for patterns in how location can affect the amount of funding a research facility receives. But at the same time, I want to have an open mind. I don't want to just limit myself to looking at funding versus location. I also want to look at other variables. Another important principle about data exploration is how data is prepared and presented affects the meaning behind that data. Every data we provide should be clear and have a logical rationale for the procedures we use to arrange and organize that data. Now, once we're able to understand how to explore this data, we want to organize our data to make them easier to think about and interpret. One of the most important things is to ask yourself, who is your audience? And how should I present it to them? After all, if I present them with an overwhelming amount of data, there's only so much a human mind can process, and we might lose them. Another important factor is organize the data with purpose will reveal patterns. For instance, if we do a line graph, this can show the correlation between two variables, and it'll be easier for people to interpret. And lastly, when we look at the results of the studies, sometimes it doesn't have to be fancy statistics that we present. Sometimes it's best to have an analysis that's explicit and concise. That way it clearly shows our purpose and correlations between the data. One of the most time-consuming tasks is organizing large amounts of data, but luckily in today we have the power of electronic spreadsheet, especially Microsoft Excel. And so these things can help you with sorting, organizing, recoding, like forming new columns, and even formulas. For instance, in my own experiment, if I want to say add all the amount of time spent on research in every single facility, rather than adding one by one, I can just type in a formula that adds it all up for me. Another thing it can help you with is graphing, like it can make line graphs, pie charts, and so on and so forth. And lastly, because a spreadsheet has limitless possibilities, you can explore with it and have fun with it, and it'll foster curiosity and make you ask, what if? So overall, in statistics, it's important to know that in order to make and present our data in an easier way to be interpreted easier, remember, statistics requires statistical analysis that discovers the patterns and meaning.
Knowing how to choose the appropriate statistic for research is really important. So first, you need to have a brief overview of the commonly used procedures. Taking Joe's test score as an example, you can always summarize the test scores using mean or average. But if it's something more general like grades, it can always be summarized using the range or standard deviation. So looking at data in only one way yields an incomplete view of those data, and you're probably going to ignore their underlying patterns and meanings. So you really want to look at the data in multiple perspectives. Moving on to the next slide. Statistics usually have two major functions. Some statistics describe what the data look like, where their center or midpoint is, how broadly they're spread, and how closely two or more variables within the data are intercorrelated. Such statistics are called descriptive statistics, which is shown by the graph here. Moving on to the next slide. The other function of statistics is known as inferential statistics. So basically, you would draw inferences about large populations based on the data collected from a relatively small samples. And you have to keep in mind that those inferences may not be accurate since you are just using one more sample to estimate the characteristic of the general population. I plan to use inferential statistics in my research because my research is about the effect of COVID-19 on the economy. It's going to be hard for me to collect the details for every country. So what I would do is to pick the most representative samples from each country and make inferences from there. For example, imagine that you are an immigration officer. Although you have never been to Egypt, you have met numerous Egyptians as they are coming in from planes or ships. Perhaps you have become well acquainted with a small number of Egyptians. From this small sample of Egyptian population, you might infer what Egyptian people in general are like. And this is an example of using inferential statistics. Moving on to the next slide. Statistic as estimates of population parameters. So parameter is a characteristic or quality of population that in concept is a constant, however, its value is variable. So as an illustration, let's consider a circle or circles. One of the parameters of a circle is its radius. So in concept, the radius is a constant. It is the same for every circle, where it's just simply the distance from the center of the circle to the perimeter. But in value, it varies. The parameter for different circle changes depending on the size of the circle. On the next slide, quantitative data analysis. So parameter is a particular characteristic of the entire population, which is really similar to the inferential statistics that I just talked about, which is why sometimes it's also called universe. We can study only a small sample of population and draw a conclusion from there. And any calculation we perform for the sample is called a statistic. So the table here is presenting a few commonly used symbols in statistical notation. Moving on to the next topic, considering the nature of the data. As you begin to think about statistical procedures that might be most appropriate for your research problem, keep in mind that different statistics are suitable for different kinds of data. In particular, you should consider whether your data have been collected for a single group or instead for two or more groups, or does it involve continuous or discrete variables? Does it represent nominal, ordinal, interval, or racial scales, which I'll be discussing later in detail? Or does it reflect a normal or non-normal distribution? Moving on, there are mainly two types of the parametric and non-parametric statistics that we're talking about in this chapter. So first, it's single group versus multi-group data. So research project yields data about a single group of people, objects, or events, or it may yield parallel sets of data about two or more groups. And remember that analyzing characteristics of a single group will often require different statistical techniques, sometimes more in detail than those for making comparisons among two or more groups. And the other is continuous versus discrete variables. So continuous variable reflects an infinite number of possible values falling along a particular continuum. For example, one can be 2 years and 1 month old or 2.5 years old. And a discrete variable has a finite and small number of possible values. So for example, one cannot be 9.2 fifth grade. They can only be 9th, 10th, 11th, or 12th grade. Moving on to the next slide. As I've mentioned there before, it's necessary to consider if the data represents nominal, ordinal, interval, or racial scales. So nominal data is just numbers when numbers are used only to identify different categories of people, objects, or other entities. However, they do not reflect a particular quantity or degree of something. Ordinal data are those when the assigned numbers reflect an order or sequence degree to which people or objects have a certain quality or characteristic of interest. However, they do not tell us anything about how great the differences are between the people and objects. Interval data reflect equal units of measurement. The difference between the numbers tell us how much difference exists in the characteristic being measured, but it has a true 0 point. So, which means a value of 0 tells us that there's a complete absence of that characteristic. And racial data, which reflects equal intervals between values for the characteristic being measured, and they also have a true 0 point like the interval data. Moving on to normal and non-normal distribution. So the graph here shows a normal distribution graph or a normal curve where we can see it's horizontally symmetrical and the highest point is at its midpoint and its predictable percentages of the population lie within any given portion of the curve. In contrast, which is non-normal distributions, there are mainly three types of non-normal distribution graphs. And the first is skewed. So the skew is the part of the distribution that stretches out a bit to one side. And as we can see from the first two graphs, is sometimes positive skewed or negative skewed. And then it's leptokurtic. So it's angular peaked, and where the highest point is not the midpoint, and we can see it's not really symmetrical. And the last one is platykurtic, where it's just angularly flat looking graph. And the percentile ranks also forms a flat distribution rather than a bell-shaped curve. And the formula here is how you calculate a percentile rank. Parametric statistics versus non-parametric statistics. So parametric statistics is when the data reflect an interval or ratio scale, and the data usually falls into a normal distribution, so everything is symmetrical. And where a non-parametric statistics is when it's used for data that are ordinal rather than interval in nature. So others may be useful when a population is highly skewed in one direction or the other, which I think really applies to my research, since for all the graphs that I have so far, they're not symmetrical, like they fall into the non-normal distributions, which is considered as non-parametric statistics.
Now let's go into detail discussing about descriptive statistics, which describes a set of data using measure of central tendency, amount of variability, and the extent of association among variables. We can measure central tendency using these methods, which includes arithmetic mean, or the fulcrum point of a set of data, the median, or the numerical center of a set of data, or the mode, or the single most occurring number in the data set. Now let's apply these methods to a potential research example to see how they are used in practice. For example, if a student is to conduct an interview that asks participants how they rate a situation from 1 to 10, and let's say the results were 1, 3, 3, 5, and 8. Now we can use this measure of central tendency to interpret the data. The first one is the mean, which would be 1 plus 3 plus 3 plus 5 plus 8 divided by 5 is 4. And the median, or the number in the middle, as we see here, is 3. And the mode, or the most occurring number in this set of data, is also 3. The next type of measurement is a measure of variability, which allows us to interpret the typical and representative data, as well as the remote and less typical data. In general, the more the data cluster around the point of central tendency, the greater the probability of making a correct guess about where any particular data point lies. We can measure variability using these methods. To begin with, the range is the difference between the highest and lowest scores in the distribution. They can be applied to data on ordinal, interval, and ratio scales. The second method is the interquartile range, the difference between the 25th and 75th percentiles. They can be applied to data on ordinal, interval, and ratio scales, and are especially useful for highly skewed data. The next method is, The next method is standard deviation, which can be used on data on interval and ratio scales, and is most appropriate for normally distributed data. The last method would be the variance, which is the square of the standard deviation. They're used on data with interval and ratio scales and are most appropriate for normally distributed data, especially useful in inferential statistic procedures. Now let's apply these methods to a potential research example to see how they are used in practice with the same example as we used above. The student is again conducting the interview, asking participants how they rate a situation from 1 to 10, and we receive the same results. Now we can use the measure of variability to interpret the data. So for the range, it would be the largest number minus the smallest number, which is 8 minus 1 equals to 7. The interquartile range would be the 25th percentile and the difference of the 75th percentile. In this case, it would be 6.5 minus 2, which is 4.5. And then the standard deviation, as we calculate it using the formula from the previous slide, would be 2.3664. And the variance would be the square of the standard deviation, which is 5.5998. The next type of measurement is the measure of association, which determines whether two or more variables are in some way associated with another. It helps us to capture the nature of the relationships and determine the strength of the relationships. We can measure association using correlation coefficient. Correlation coefficients for any scatter plots are in the range of -1 to 1. A correlation coefficient for two variables simultaneously tells us two different things about the relationship between those variables. The first one is direction, where we determine if the coefficient is negative, then the slope of the graph is negative and vice versa. The second one is strength, meaning that the closer the absolute value of the correlation coefficient is to 1, the stronger the correlation between the two variables. And the special reminder is that correlation does not indicate causation. And we can apply these methods to a potential research example. So for example, if a student's research is about to what extent family income correlate with math performance skills, which is similar to my research, we can use a calculator to find the correlation coefficient. And let's say we find that it is 0.9. And this would demonstrate that the family income and math performance skills correlate in a strong positive pattern. And then we can find that the 81% of the variability in reading ability is accounted for by the variability in age. As we can see here, this would require a bit of math. And then with the math that we use to determine the correlation coefficient, we can interpret it using these different ways.
Next, we're going to go more into inferential statistics. Inferential statistics allow us to draw inferences about the larger population. For instance, in COVID, we can take samples of a large population from random sampling. There are two main functions of inferential statistics. The first one is to estimate a population parameter from a random sample. The second is to test statistically based hypotheses. Now, let's go on to estimating the population parameters. Inferential statistics can tell us how close sample statistics are to the overall population. It estimates the population by one way is seeing the relation between the central tendency or the mean, or seeing the relationship with the variability, the standard deviation, and seeing the relationship with proportion. Now, all of these estimates are assuming that the sample is randomly chosen and representative of the entire population. I can incorporate this in my own research on, say, the clinics that receive funding, and I can investigate on one facility and compare it to the overall population of other facilities. Sometimes there will be errors in the estimations we make. Now, this error doesn't mean a negative connotation. It just means that there's a difference between the population mean and the sample mean. What we know about this kind of error is that the means we might obtain from an infinite number of random samples can form a normal distribution, or that bell curve. Secondly, the population means equals the mean of all the samples. And third, the standard deviation of this distribution of sample means is directly related to the standard deviation of the variables. Another kind of error is the standard error of the mean. This is the standard deviation for the distribution of sample means. It can tell us how much the particular mean we obtain is likely to vary from one sample to another. Below are some formulas that may be helpful to us when calculating the standard error of mean. Now, once we tackled all of these errors, we want to see what kind of ways can we estimate. So there are two types of estimates we can make to estimate the population. The first one is what we call a point estimate. It's not precise and doesn't correspond exactly with the population, but it's a single statistic that can help us estimate it. So let's give you an example. Say I take a sample of 100 pins from 500,000 pins and measure their diameters. I can find their mean and standard deviation. Let's say the average diameter is 21 millimeters, and the standard deviation is 21.02. I can then conclude that and say that the average diameter of 21 mm is representative of the entire population, 500,000 pins. Although this average is not the exact average of all 500,000 pins, it's better to have some data than none, and we can apply this to any of our research. Now, the second kind of estimate is an interval estimate. This one is a more accurate approach. In here, we specify a range within a population. In other words, we state the probability that it actually lies in a particular interval. This particular interval is what we call a confidence interval. Now, going back to our previous example, we want to incorporate this. We can say that the company has produced the diameters between somewhere 21 and 21.02. That is the range we are defining, our confidence interval. And then we can say that our standard error of the mean is 0.02. Now, we just first discussed the first major function of inferential statistics, which is estimating a population. The second one is to test hypotheses. Note, the hypothesis we are accustomed to is what we call a research hypothesis. It's one where we find a problem and a solution. We do if, then statement. The one we are investigating today is statistical hypothesis, which is also called null hypothesis. In a null hypothesis, we want to consider whether or not the results were due to chance alone. And we do this by comparing observed data with results. So how do we know if the result has not occurred by chance alone? Well, we use what we call a 1 in 20 probability, which is where we claim that any result that would occur by a chance of only 5% of the time would probably not be due to chance. Sometimes, if we want to be more rigorous, we can use what we call a 1 in 100 criterion. So rather than claiming a 5% would not be considered chance, we can say a 0.05 or 0.01. Any number is up to us. So we can decide whatever number we want, and this is what we call a significant level. Any number we choose will be the significant level, and will determine and define what we define as chance. Now, anything we deem not due to chance is what we call statistically significant, and anything not due to chance, we reject the null hypothesis. Sometimes, or maybe most of the times actually, in the results section of any researcher, they usually state their significant number, or that alpha level we mentioned earlier. For instance, a researcher may say P is less than 0.01. This just means that the experiment will occur by chance less than one time in 100. Another example would be, say, P is less than 0.003. This would mean the difference will only occur 3 times in 1,000 of the population. Overall, we provide a certain narrow margin of variation and chance within our data. When it comes to estimating and forming a hypothesis, there are two types of errors that we often make. One of them is the type 1 error, which is where we incorrectly reject the null hypothesis and we erroneously conclude that a result was not due to chance when in fact it really was. The second type of error, the type 2 error, is the opposite of that. We claim our results are due to chance when really it wasn't. So how can we decrease the odds of making a type 1 or type 2 error? Well, we want to have a larger sample size. A larger sample size means the statistics will less likely diverge from our population. We want to maximize our validity and reliability. And we want to use parametric rather than non-parametric statistics because non-parametric statistics typically require large samples, while parametric techniques are more powerful. Now, going back to our comparison with research hypothesis and statistical hypothesis. Back then, we're familiar with forming a solution or discovering something that was undiscovered. In statistical hypothesis or the null hypothesis, we want to interpret data. So, in order for success within this quantitative data field or statistics, whatever statistical technique you choose, make sure you know how to thoroughly do that approach. This will lead you to success in understanding how to solve your research problems and forming a defensible analysis. Now, going on to a different approach, there's another option where what we call a meta-analysis. So sometimes rather than analyzing and drawing conclusions to our own data that we collected, we can instead analyze and draw conclusions from other researchers' statistical analysis. This is what we call a meta-analysis. And I myself can apply it by researching, say, on other clinical facilities conditions that were already published. Meta-analysis is rather than verbally describing how studies contradict others or how they are having inconsistent findings, meta-analysis presents a statistical study. So first off, meta-analysis researchers look for a fairly extensive search relevant to their topic of interest. Secondly, they narrow down and find the most appropriate studies to assess. And third, they convert the study's results to form a common statistical index. Thank you.
Earlier in our presentation, we mentioned that general purpose spreadsheet programs can be used to describe and analyze sets of quantitative data. However, many spreadsheets are limited in their statistical analysis capabilities. And as an alternative, you may want to consider using one of the several statistical software packages not widely available for use on personal computers. And such packages have several advantages. So the first one would be range of available statistics. Many of these programs include a wide variety of statistical procedures, and they can easily handle large data sets, multiple variables, and missing data points. The second would be they are user-friendly. So as statistical software programs become increasingly powerful, they also become more user-friendly. In most cases, the programs are logical and easy to follow, and results are presented in an easy-to-read table format. However, selections of the proper statistics and interpretations of the results are still left to the researcher. So you shall get to be the one that decide what to include and what to exclude from your research. On the next slide, assumption testing. So a common feature of statistical software packages is to test for characteristics. For example, the skewness or kurtosis that might violate the assumptions on which a parametric statistical procedure is based. And the graphics. Many statistical programs allow the researcher to summarize and display data in tables, pie charts, bar graphs, or other graphics. But remember that computers should not do it all. You as a researcher should know why are you doing the calculations, the purpose of it, and how to include the statistics and the calculations in your research in your own way.
We have learned a lot about how to interpret data using statistics. But what is the purpose of interpreting data? It helps researchers to capture all the nuances and meanings of the data in relation to the research problem. The steps that we can take to interpret the data include relating the findings to the specific research questions and hypotheses. Relate the findings to pre-existing literature, concepts, theories, and research studies. We can do this by confirming a current theoretical perspective, cast doubt on common knowledge, or simply raise new questions that must be addressed before humankind can truly understand the phenomenon in question. Next, we can determine whether the findings have practical significance as well as statistical significance. And practical significance is whether findings are actually useful. And finally, we can identify the limitations of the study. And that concludes our presentation for today. Thank you for listening, and we hope that you have learned something new.